In this video, I'm going to show you how you can complete an ANOVA table with all of the quantities you need. Okay, let's jump in. So, what we're seeing here is the actual table, and I have some sample data that I've put together here. You can see that I've got a control group here. Let me highlight this. I've got a control group. I've got apples, kale, spinach. So what I'm pretending is that let's say the Penn State football players really need to work on their speed. That's not the case. They're awesome. But let's pretend that they do need to work on their speed. And so one of their coaches, their conditioning coach, is telling them that they're going to be given an extra supplement of apples, kale, or spinach. And then they're going to measure them to see how many miles they can run in a 2-hour period, let's say. Okay, so the control group, this group here, is given no extra food items. They just eat their standard diet. Apples, they're given a whole bunch of extra apples. Kale, likewise, and spinach, likewise. And there were 4 different people inside of each group. So we're seeing that here on the side. And we know there are a total of 4 groups. So we ultimately have 16 participants. Okay, so 16 participants. We need to determine if there is a difference in means for each of these groups. We do that with an ANOVA table. So let me come back over here. I'm going to zoom out a little bit so we can have some space to work. So the first thing that I want to do is fill in the degrees of freedom inside the ANOVA table. So to do that, I'm going to zoom out just a little bit further here. You can see that we have treatments, errors, and totals over here on the ANOVA table. Then we're going to have degrees of freedom right here that we're going to need to fill in. The way that we do that is, so we know that we have 16 participants. The total of degrees of freedom for an ANOVA table is always just, it is n minus 1. So n being 16, 16 minus 1 equals 15. We're going to put that right in here. So 15 is the degrees of freedom for the total group. The treatment group, the treatment degrees of freedom, is simply the numbers of treatments, and we have 4 of those. We've got control, apples, kale, and spinach. So it is, treatments we'll say is k minus 1. So 4 minus 1 is equal to 3. So degrees of freedom for treatments is 3. And then for the error grouping, we simply take the total degrees of freedom and minus out the treatment. So 15 minus 3 equals 12. I'm going to center that here. So we've got 12. Okay, that is how we find the degrees of freedom. Let me clean some of this up. Now what we need to do is we need to get into calculating the sum of squares, which we'll do here, and the means of those sums of squares, and then the F statistic. Let's jump right in. So in order for us to be able to calculate the sum of squares, we need to do some labeling on our data over here, just so you are, so it's very clear what we're doing here. Okay, let me clean this table up a little bit first. Now, let's pretend like a single observation is represented by a y, as it would be. So our response, y, is going to have some subscripts, I and j. I is how we're going to represent our actual treatment. So i's go up here. So I equals 1 here, I equals 2 here, 3, 4. And J is the jth participant within that treatment. So J over here, J equals 1, J equals 2, dot, 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 J equals 4. Okay, so let's pretend we want to identify an individual in the test, the second participant that was in the KEL treatment group, so 14.5. We want to identify them. The Yij that we will use for that individual is Y. I is 3, so subscript 3, and J is 2. That is how we would specify that. Sometimes you'll put a comma in there. You normally do want to put a comma in there just because 3, 2 could be interpreted as 32. And we know that that is equal to 14.5. Okay, so that is some labeling methods we'll be using as we complete the ANOVA table. And the first calculation we're going to find is the sum of squares for the total group. So we're looking for this value right here. Okay, and how we find that, let me zoom out a little bit here. Okay, so how we find that sum of squares for, zoom out a lot. Okay, how we find the sum of squares for the total group is as follows. So total sum of squares is equal to the sum of the y value, the observed y value, so that's going to be Yij, these are the individual observed values, minus y hat, the grand mean. That is depicted as a y hat with 2 dots. Okay, 2 dots mean that it's inclusive of all i's, all j's. And then we're going to square that difference and sum them all up. That is how we get the total sum of squares. So let me give you a quick example of what this means. So if we look at y 1, comma 1, it is equal to 10. That is this value right here, okay, in the control group. So y equals 10. So what we do here, first of all, we need to we need to find y hat, the grand mean. So not y hat, y bar, the grand mean. And to do that, we need to sum up all of the values, all 16 participants' values, and then divide by 16 for the mean. So I'm going to do that really quickly, and then I'll get back to you. So the sum of all these values is 220. If we divide that by 16, it comes out to 13.75. Okay, so y bar, the grand mean, is 13.75. Okay. So now what we're going to do here is we're going to take 10 minus 13.75, square that, and then add it to the next one, which is, we're just going to go down through the control group, 9 minus 13.75, square it, plus 8.5 minus 13.75, square it, and so forth, all the way until we get to the last observation, or the last participant in the spinach group, which is 16. 16 minus 13.75 squared. I'm going to calculate that. So I've taken all of these values, added them up, or I've taken them all 10 minus 13.75. We know that is negative 3.75, and then we square it. That works out to be kind of a gnarly number, 14.0625. Then we do the same thing for all of these numbers. We add them all up, and the grand sum is 104. So the total sum of squares for the full set is 104. Now we are going to find the treatment. To do that, I'm going to clean this up. Let's see here. Select that and delete it. And you know, I realized I actually don't want to delete that. I want to keep the these variables here. Then we're going to delete the rest. We're going to write out what the treatment sum of squares. So, I gotta switch the pen. Treatment sum of squares. This is equal to the sum of this group here. So what we do is n I, and this means n is the number of I being the participants within an individual control group or apples group inside of a group. So the ni is actually going to be 4 because we have 4 participants inside each group. We're going to multiply that by the y bar of the I minus the grand mean y bar. We're going to square that. So we're going to take this, let me see here. We're going to take this first portion here. We're going to square it, then multiply it by ni, which is 4. Then we're going to sum all of that up. So let me do a calculation here on just this little piece. And to do that, we need to find the mean within each of our groups. So the mean for 10, 9, 8.5, and 12.5 is 10. The mean here for the apples is 15. And the mean for the kale is 14. The mean for the spinach is 16. Okay, so we know what the y bar I is. Let me zoom in more here to make this clear. So y bar I is equal to 10, 15, 14, and 6. So we're partway there. What we're going to do here now is we're going to take the y bar I, so 10 for that first group, minus out this piece here, the grand mean, 13.75. We're going to square that, and then multiply by ni, which is 4. And then we're going to add that to the next one, which is going to be 4 times 15, the mean for the apple group. Subtract the grand mean of 13.75, square it, and so forth. Okay, so I'm going to do those calculations here. So once we take the differences, we square them, multiply them by 4, and add all of that up, our grand total is equal to 83. So we're going to go ahead and write 83 there in the sum of squares for, that's for the treatment. And then what we do is to find the error sum of squares, that is equal to the total sum of squares minus the treatment, total treatment sum of squares. So 104 minus 83 is 21. So our error sum of squares is 21. Okay, and then filling in the mean squares is relatively easy. We're actually finding the mean of, so let me zoom in here. Let me delete some of this first. Okay, the mean squares for the treatment set is going to be simply the sum of squares. Let me get my right pen here. the sum of squares divided by the degrees of freedom. Okay, that is how we find the mean squares. So let me actually write that down for you. So sum of squares divided by degrees of freedom is equal to the mean squares. So if we do these calculations, we're going to have 83 divided by 3 equals, and this is the mean squares of the treatment group. Mean squares of the error group is going to be 21 divided by 12. And I'll calculate these. So I've done these calculations. 83 divided by 3 is 27 and 2/3. Okay. And the mean square of errors, 21 divided by 12, that is simply 1.75. So we're going to put these where they belong. So 27.67 and 1.75. Then calculating this last field, the F statistic, is also quite easy. Let me pull up the pen. To do that, we divide mean of squares treatment by mean of squares error. So 27.67 divided by 1.75. Let me do the math here. 27.67 divided by 1.75. That is equal to 15.8114. We will put that here. And then we're going to compare that to a F statistic table in the back of the book, or I will show you here. And what we're going to find is if this F statistic is larger than what we have in the F table, we know that there is statistical significance to say that the null hypothesis is not accurate. The null hypothesis is, in this case, let me zoom out. I'll just come over here. The null hypothesis is that there is no difference between the control group, the apples, the kale, and the spinach. So the way we would write that is the null hypothesis is that control is equal to apples is equal to kale is equal to spinach. That's a really simple way of writing this. That's not how you normally write it, but it is a very simple, understandable way. And we are trying to determine if that is true. If this degree of freedom is greater than, if this 15.8114, sorry, if the F statistic is greater than what we find in the back of the table, then we know we should throw out the null hypothesis. So I've got one pulled up, and what we're going to do, there's two numbers we need to remember for this F statistic. Let me get the right pen here. Okay, so our critical F is going to be, to note it like this, F of alpha. Our alpha is going to be, let's just say it's 0.05. That means it's a 95% confidence interval we're working with. So how we state that is F of, and you put small parentheses here, subscript parentheses, 0.05. And then we're going to separate that by the degrees of freedom. First, the treatment degrees of freedom of 3, and then the error degrees of freedom for 12. These are three numbers that we need for the F table. Let me pull up that F table. This is an F distribution table from UCLA. And, I cannot, let me see here. I'm going to have to move my window here. Okay, I've changed the pane so that we can see this. We're looking for degrees of freedom 1 at the top here. This degrees of freedom 1 on the top row. We come over to the 3, and then we're going to come down to degrees of freedom 12. So the top row of my pen won't work here since I'm on a web page. So what I saw was I couldn't highlight anything on the web page, so I copied and pasted that portion of the F table and brought it over here. And what we're going to do, so we know our degrees of freedom for the treatment group. The first value is 3. So we come over to 3. Then we know that the second value is 12. So we're going to come down till we hit 12 on that second degrees of freedom. And this value right here, 3.4903, that is our degree of freedom. So let me write that. Oh, that's not our, sorry, that is not our degree of freedom. That is the F statistic we're going to test against. So F for our critical value of 95% confidence is equal to 3.4903. And in this case, where our F up here is 15.8114 greater than this F statistic here, we know we can reject the null hypothesis, and there is some difference between the means here in our 4 different groups. And that helps us get started in our journey of research.